So it's my great pleasure to have Roberto Morabito speaking here today. He's currently assistant professor in the communication systems department at Eurecom in France, and his research focus is currently on network systems, edge computing, and distributed AI. Also, he is exploring the role of generative AI in constrained environments. He's actually a local, so he holds a PhD from Aalto University and has held positions at Ericsson, University of Helsinki, and visiting positions at Princeton, INRIA, Munich, and Yale University. So we are very happy to have you. Please take it away.
Thanks a lot for the opportunity, Alex. And it's pleasure as an alumni always coming back to Finland, and especially in Aalto University. I've been actually spending nearly 10 years here in Finland. So, and it's always nice to get back, especially with such a kind of weather that helps. You never know what you can expect in April, especially. So the goal of today, and I was already mentioned to Alex during our discussion that we have had before the lecture, is trying to provide an overview about the research activities I've been conducting the last few years. And you won't see much further learning, and also not much math, but it's going to be pretty much a lecture that has heavy implementation and real deployment focus. I've been, however, added a few insights on possible overlaps that these topics I'm going to present have potentially with further learning. So, so I would say that that's pretty much the goal of today, and feel free also to interrupt me during the lecture. We don't necessarily need to wait the end of the lecture if you have any specific question or something that is not clear enough. But I will talk mostly about this sort of edge cloud continuum. We will see, especially when it comes to the lifecycle management and provisioning of AI inference from different perspectives, from the edge computing to the cloud. I will shortly introduce also what's edge computing about, if that's not not known to everybody here, and then little by little trying to go through these different topics that I have for my presentation today. As a first thing, I would like to spend some time and discuss about this area of distributed AI in the context of edge computing, which is pretty much the area that is kind of the connecting node that is sort of putting together the different research activities in the last few years. And let's try first to define what's edge computing about. I'm sure that everyone is familiar with cloud computing. We use cloud computing nowadays in a lot of services. I mean, already many university services are relying on cloud computing from our storage, document storage, email, possibly, you name it, right? But obviously there are many limitations connected to cloud computing. Here's a few examples when, because of mostly network error, we are not able to reach a specific cloud service. Here, just an example for us, like Google Translate, Netflix, and I guess that nowadays the biggest nightmare that everyone perhaps can have is to get this type of error, ChatGPT not available because some network error. So that's sort of hints on the fact that the cloud dependency for many services nowadays is very strong. So already back in 2015, 2016, when edge computing wasn't really a big research topic, I started to investigate in this area. And just to give you some context, that's pretty much where we can locate edge computing in this sort of three-tier architecture, where we have the device layer like our smartphone, for example, but smart car, smart robot, any kind of end device that can belong to scenarios like smart manufacturing, smart cities, etc. And then in between this device layer and the cloud layer, we have this additional edge computing layer, where the dependency from the internet, from the connectivity, is way more reduced, and there are additional advantages, especially when it comes to latency, obviously, as I just mentioned. One big aspect, one strong selling point also about edge computing is the security and privacy aspect, and that's also some overlap with federated learning, because the majority of the data stay confined in sort of federation of edge computing, and that's obviously a big advantage compared to giving away your data that you are generating in your devices. So this is just to set the stage respect to the concept of edge computing. And one specific area I've been focusing in the last few years is the sort of intersection that we have between edge computing and artificial intelligence, which is commonly defined as edge AI. You might find a similar definition as edge intelligence. There is always this, for anything, there is always this sort of definition dilemma, but pretty much the idea is trying to study and the different aspects that stand at the intersection between edge computing and artificial intelligence, machine learning, etc. One other aspect that also is driving my research is, as I mentioned, the practical development and deployment of different proof of concept. And during my PhD studies, I start already, when looking at edge computing, I was particularly interested on scenarios where the computing capabilities of the devices are particularly constrained. So edge computing can be a single board computer like a Raspberry Pi. It can be our smartphone. That's sort of the area that I'm particularly interested in. I've been looking mostly in my research. You can find also edge computing defined as a powerful micro data center or server machines. That's least interesting for me. So I've been focusing mostly on this sort of area where the constraint in terms of computing and networking are much more emphasized. And when approaching this area, I looking at especially the trends that are in terms of edge AI chip development. One interesting aspect was that beyond the general consumer devices like smartphone, tablet, there was a boom of enterprise edge devices. Just to give you an idea, when I talk about edge compute, and in this slide you can see that it was in proportion the area that was growing the most in this time frame between 2020 and 2024. Even more respected the smartphone area. When I talk about enterprise edge, I'm also talking about this type of devices. I'm sure that everyone is familiar with devices such as Raspberry Pi, but nowadays there is possibility of deploying efficiently and with very good performance AI algorithms and AI application on this type of single board computer, which are a little bit more advanced respect to Raspberry Pi, to the extent which they also embed some sort of AI acceleration. It's well known that AI heavily relies on GPU in the cloud, but also actually on this type of edge computing devices. But GPU is not the only way to perform AI acceleration in edge computing. There are a bunch of other accelerators that are nowadays available. Just to give you an example, in the center, the device in the middle in this slide is a device produced by Google, which embed a tensor processing unit. So it's specialized to perform specific operation, and the one on the right has this VPU, vision processing unit, which is particularly optimized for computer vision tasks. So as you can see, this sort of enterprise edge perspective from device perspective includes also a certain degree of heterogeneity. And also, just to give you an additional element on how impactful this AI acceleration became and has evolved in very short time, between 2019 and 2024, there was a very interesting article in 2019 by Facebook, where was provided a very extensive analysis on how AI inference was performed in smartphone. And the majority of the AI inference at the time was performed actually on CPU. There wasn't just a few years ago, there wasn't any AI acceleration happening in our devices. In 2024, just a few months ago, Samsung was announcing the Galaxy S24, and this is just an example, embedding a very powerful AI accelerator, like the ones we have seen in this slide, capable of running any type of almost AI application, including a generative AI application. So this type of device perspective and heterogeneity perspective was something that triggered my interest. And also my background is network system. So the network aspect has been always relevant in my research. So when I start to look a little bit on the from network perspective, I was also mostly considering the AI inference aspect, and that's the reason is because compared to the training, the sort of real-time requirements are much stronger, right? You could consider, for example, autonomous driving application where you have a very strong constraints. I'm getting actually to that in terms of latency, and any type of processing, including AI, must be confined within a certain threshold. So I was trying to put the pieces together, heterogeneity, devices, the network, and I started realizing that when looking at AI inference in distributed edge computing system, there wasn't really much research in areas where these different aspect, the networking aspect, the heterogeneity, multiple edge nodes at once were considered. And also especially the networking aspect. So the type of scenarios that were analyzed were pretty much looking like this, right? A cloud, perhaps one single edge device, one end device, very simple AI inference processing happening in this type of schema, similar to what we have seen before when introducing edge computing. But what was missing in practice was a system that was a little bit more complex, which is somehow aligned to what in practice happen in real deployment scenarios. The typical example I bring here is the smart city, where you have a high level of heterogeneity, high scale in terms of end devices, of edge nodes. You could think about drones. You can think about in autonomous driving something like a roadside unit, telecommunication base station, etc. So this type of scenario was somehow under-researched. And the main question I wanted to ask is there a way to optimize the resource allocation of AI inference in such complex scenarios? It's not a trivial question, because, as I mentioned, there are multiple aspects that we need to take in consideration. First, as I mentioned, the latency component. We do have obviously the computing latency, the one that is due to the AI inference computation itself. But then we have also these communication latencies that you can imagine in scenarios like this one, where you have a multiple connection between different nodes, between the edge nodes and the cloud, between the edge nodes and the end devices. It's very tricky to consider. And the significance is that nowadays this application, like voice assistant, but also this autonomous driving, have like by standard very strong requirements: 200 milliseconds, 10 milliseconds in the case of autonomous driving. So very strict requirement. And the other important is, of course, requirement is obviously reliability. We can't somehow afford that our system is mostly down. We need to be able to have a robust fault tolerance mechanism when we are dealing with this type of system. We need to somehow ensure that our AI inference services can be provisioned in a sort of seamless fashion. So these are somehow type of the reliability and network and the latency are somehow fundamental requirements that are coming in the moment you want to develop this type of system. But then in practice, when you need to put together all these pieces, there are additional requirements that are due to the practical development of such a system. First, you would like to have a system where you can integrate the devices that I showed before in a sort of plug and play fashion. So I don't want to necessarily use only GPU or only TPU or any other kind of accelerator. I would like my system to be as versatile as possible. And especially when it comes to highly fragmented and heterogeneous scenarios, I also would like to have a system that allows me to get AI inference services, and I have a practical example coming soon, AI inference service regardless of the node that at the edge that will compute it, right? For me as an end user, if I'm asking as an autonomous driving device, let's say I'm asking some service to the edge, for me, it doesn't really matter whether it's a GPU or a TPU or a VPU that provision that kind of service. For me, what matters the most is that we have a reliable service. We have a latency that is confined within this, which below a certain upper bound, etc. That's the most important requirement, and that obviously implies that we need to sort of introduce a combined computing and networking orchestration techniques for ensuring that these requirements in terms of downtime and fault tolerance are ensured. So the scenario, as you can imagine, is particularly complex, and partially during my postdoc and also during the last few years of my employment at Ericsson, I started to work heavily on this area, and we developed a testbed which has actually been used for several works that was essentially combining the type of devices that I've been showing you earlier. Because my goal was to try to understand also how heterogeneity can possibly affect the whole AI inference provisioning in such kind of scenarios. So these type of devices, different AI architecture, constrained in terms of memory. As you can see, there's no any device that has a higher RAM memory than 8 gigabytes. Actually, there is some device with just 1 gigabyte and very limited storage. So the constraint in terms of computing capabilities are quite substantial compared to, for example, server machine. So this was like, okay, let's have this bunch of devices and let's build this kind of system, right? But then the reality is always a little bit different because this hardware heterogeneity actually has a big impact in terms of there are some implications not only from hardware perspective, but also from a software perspective. And the reason is because each of these modules essentially require dedicated sort of lifecycle management for the machine learning models. Just to give an example, you cannot take out of the box a TensorFlow model and make it running in any of these boards. You need to make some heavy lifting processing and model conversion processing in order to adapt the models to be executable in this type of devices. So this hardware and software heterogeneity has measured implication, has had a measured implication in my plan when thinking of developing such kind of system. The first thing was that it was pretty much impossible to have a out-of-the-box device interoperability. I cannot make these devices talk to each other unless I build something on top of it. The second thing was that the AI inference latency can vary from board to board. The execution, because of this different type of optimization that we have in this AI processing, we have essentially the implication that we don't necessarily have a same AI inference if we are running an algorithm on a GPU or in a TPU. So this is something else that must be considered. And then last but not least, when looking at distributed environments, there's no somehow, again, some sort of out-of-the-box way to offloading the execution of AI inference from one node to another. So these were three big implication that this hardware and software heterogeneity were bringing in this context. So the scenario turned out to be extremely complex. We need to essentially have, we need to keep in mind the whole picture, right? We have heterogeneity in the nodes. We can have a different type of computational capabilities in the node. We might have in a real network nodes that are overloaded in a certain moment and we cannot use them for performing a certain task. We do have the network latency in between, latency which is highly variable. It's not easy to just take a sample of latency. It might vary, it has high variance, right? So it's extremely complex to trying to define from an end device perspective, what's the best node that can provision this type of AI inference service. So the example I'm going to bring shortly is essentially my end device, very constrained, cannot run any processing, is requesting an object detection service. The question here is which AGI node is the best in the best position for ensuring the quality of service that I want to have for my own application, taking in consideration all these different trade-off. So in order to overcome the limitation that we have seen, we have been working for developing essentially a software architecture which was heavily decentralized. So there wasn't any central node, and we were able to create a sort of a wrapper on top of this heterogeneity from hardware and software perspective. What you're seeing here in this provisioning agent component, you have a way for moving the execution of services from one place to another. You have a way to overcome the heterogeneity. To me, all the inference provisioning can be given by any type of node, regardless of the underlying architecture, etc., etc. So we developed this relatively complex system because we had a different component. You can also see this AI model management component where we were converting the model in an automated fashion from in order to be suitable to the targeted node. So we give a TensorFlow base model, and then we get the corresponding GPU, BPU, or TPU model. And what we decided to do was to actually build and test this system in a real testbed deployment. We were also emulating some real trace, 5G network trace for when it comes to the network latency. So just to give a bit of context, the end devices in this case are normal Raspberry Pi, which were sending some video streaming to the edge, and then the edge under certain dynamic and aleatory, basically computation requirements, were in an automated fashion deciding, thanks to the implementation we did, deciding what was the most suitable node to execute the AI inference service. And this is just to give you a practical idea. I have a short video soon coming, but the idea was that, right, we send, for example, a streaming video from my drone. You can think, for example, about a drone that is not able to compute AI inference locally. I will essentially the system was built in a way that in an automated fashion, the execution of the object detection was demanded to the node that was in the healthiest status from network perspective and from computation perspective. Then what is happening is that for some reason, the quality of service requirement cannot be met anymore in the node that is executing that service. The provisioning of the AI inference is seamlessly moved to another node, still in order to ensure this quality of service. And the reason can be because this device on the right gets some other application to be processed, or the network latency between the drone and the edge device becomes so big that the quality of service is not satisfied anymore, and so on and so forth. There are obviously multiple reasons. And that's the short demo I would like to show you. Essentially, we have an object detection of a real-time video streaming. So we have this Raspberry Pi transmitting some video streaming. We have some footage from New York City, right? We are performing object detection in the Coral Dev board, which is embedding this tensor processing unit. As soon as the node is overloaded, the execution of the inference is essentially migrated to the NVIDIA Jetson Nano. We developed a nice system where we had, full, here on the left, you can see all the nodes in the network from the cloud, the edge devices. Is not very visible, but I can share the slides afterwards. And also the end devices. On the right, you can see we build this sort of network latency matrix. Basically, each node was fully aware of the network latency situation respect any other node. And I was essentially using a very simple time series forecasting algorithm for trying to understand what was, for ranking, what was the best node around in terms of network latency. And then we were measuring, so the computation, the inference itself, the AI inference itself, and the networking part. So just to show you what is happening here, we have this object detection running on the Jetson Nano. And what I will show you is that as soon as the quality of service requirement, which was set in this case to 200 milliseconds, was for some reason violated, the execution of the AI inference is automatically migrated to the Coral board, which is embedding a completely different AI accelerator. So we are not using the GPU. So right, you can see the object detection is running. Then on the right-hand side, quality of service requirement is violated, and automatically the AI inference execution is migrated to the node on the left. And this is basically without stopping the service. We have been migrating the execution from a GPU to a TPU. No matter of the type of AI accelerator we are using, we are still able to get this service up and running. And one interesting other aspect that we were also figuring out, and something related to what I mentioned earlier, was that we realized that each board was essentially providing different type of performance in terms of scale. You can see here that we are running different object detection instances on different type of devices here in the bottom left, and for different type of input frame size from the video with different resolution, like 600 by 600 and 1200 1200. And the reason why we get different, so they don't grow the same way with the higher number of instances. The reason is because the life cycle of how the actual AI inference happen in each of the device is extremely different. We have on top basically a set of different operations which are bouncing between the CPU and the GPU, TPU, VPU, and that basically affects the performance that we have. So this somehow force us to brought us to consider the orchestration in a bit more complex way, because we can't treat the devices in the same way. We need to essentially give different weight to the AI processing done in one device with respect to the other, based on the type of scale, based on the type of instances that in that particular moment the device is running. Essentially we came up with this sort of need of having different dynamic adaptation of the workload. In this sort of weighted formula that we are having here, we have essentially the weight of the CPU, which is completely the computation is basically divided between CPU and the AI component, and then obviously we have also the networking aspect, which must be taken into account. And essentially with this alpha, beta, and gamma, we can give weight, different weight, based on the requirements that my application has, or based on the requirements that my edge computing wants to process, right? If I want to give more weight to, in a dynamic way, to application which use more CPU, I will of course emphasize alpha. Vice versa, if I want to give more weight to the GPU-based processing, I will act on beta, and etc. Also for the network perspective. So here's perhaps the first kind of a possible intersection as a follow-up from federated learning perspective, because obviously these alpha, beta, and gamma can be federated based on the local execution. You have a different type of processing, a different type of requirements, etc. So this could be, for example, one way to enhance this work from federated learning perspective. Think about training some very simple algorithm locally, where you can decide and get the optimal setup for these different values, right? And this was pretty much, I dedicated quite a lot of time on this work. I wish to have dedicated much more time. There were a lot of interesting things to be taken into account, especially when it comes to the offloading. If you think the offloading in this case comes for free, but you could think of many other extensions where you can actually include sort of incentive mechanism to the other nodes, right? Why I need to borrow your resources as edge node? So you could think of a reinforcement learning based extension of or very basic incentive mechanism, etc., etc. So if anyone is interested in looking into this, I would be happy to discuss. And we do have actually the testbed that you have seen. I was able to replicate it here in the University of Helsinki with much higher scale. We do have approximately 40 to 50 devices with different computational capabilities. And here just a few references about this work. And what I would like to do next is looking a little bit on something that I've been doing. Of course, feel free to interrupt me if you have any question until now. Yes, please. Yes. Yes, basically the system that we were using for orchestrating everything as this, it was using a technical, it's called the sidecar proxy. Essentially on top of the application, we were adding another security layer that was making sure that the communication was secured, encrypted, etc. So that was basically built in we were using in particular MTLS, this it's quite a well-known protocol. So that's how the security in practice was ensured from the networking point of view there, and how obviously like there is some other aspects from data perspective. Here, the assumption is that obviously that you trust each other when you can offload to another device, right? But that's obviously a different story. That would be another trade-off that should be taken into account, obviously. But that's perhaps another federated learning related area that would be worth to investigate. Any other question on this part? If not, just I would like to discuss a little bit on some activity that I've been recently doing in the area of generative AI. Again, the scenario are pretty much similar. The goal here was to try to understand whether there was any possibility of looking at generative AI in this context as well. There is already a lot of activities ongoing. You can easily already look for different activities in where there is this sort of intersection between large language model and IoT, autonomous driving, running a language model on edge devices, etc. So we start to work on this already some time ago, before the big wave came, and the main motivation was that along with a bunch of generative AI models that are coming basically daily, right, the big ones, right, there is also a set of language model that we define as a small language model, which has had an equally bigger explosion. So nowadays, this is a figure that shows the sub 4 billion models, and this is just a small subset of models that nowadays can easily run, more or less easily, run on a smartphone or in the type of devices that I was showing earlier. And the other reason that somehow pushed me to look at generative AI in this context was due to the fact that when you look at AI inference in cloud-based services like ChatGPT, API from OpenAI, etc., the actual cost is very high. If you think about hyperscale scenarios where you have multiple devices, you have continuous connection, continuous requests. So we shouldn't think about our daily usage of this type of service, but whether it's a smart city that is continuously trying to pull some information from API or GPT models, the cost can become extremely high. So we start to look at these different activities, and there are essentially three main threads I'm following at the moment. The first one was a work that we did with a master thesis student here, University of Helsinki, and which was related essentially on benchmarking small language model in constrained devices. So we were originally we start to look at whether this is feasible, to what extent, is it really possible to run a language model in this type of devices. And originally we were also very ambitious because we wanted to look at running generative AI models on microcontroller. So something even more constrained. I will get soon to that as well. But then we had to limit our area to devices similar to the ones that we have seen earlier in the previous work. So mostly single board computer. I won't spend much time discussing about this work, but we did a very extensive benchmarking analysis using Raspberry Pi and NVIDIA devices, so embedding a GPU. At the moment, there's no any support for any other AI accelerator that you have seen in the previous part of the presentation. And the type of analysis that we have done was to take in consideration different quantization, different small language model. We tested up to 11 small language model, the trade-off with power consumption, how impactful are the different power modes in the different nodes, etc., etc. We come up with very extensive benchmark work. We have a preprint published on related to this. And well, the title is a kind of self-explanatory because there are still, it's definitely feasible to run small language model. And we run also some qualitative benchmark analysis. So not only quantitative, because the quality of the answer from language model is also very important. So we did a very extensive, the paper is currently under review. But just to do, as I mentioned, we tested the 11 language model, different type of quantization, CPU-based execution, GPU-based execution, trade-off with the power, trade-off also compared to executing the language model in cloud. So if we, in theory, would only rely on language model, would we be able to have a favorable trade-off in terms of quality, power consumption, even considering the power cost of electricity, and so on and so forth. So if you're curious about looking at this type of number, have a look at this publication. And so this was one big aspect that we wanted to take in consideration. And the other one was looking at a language model, how actually large language models, so no small large language model, could help in the lifecycle management of those devices that we have seen earlier. So these different edge AI devices. We want to, in practice, look at this intersection. Like, is there any possibility of doing something at the intersection between large language models and edge AI? And you can see here also that I added the TinyML because we were particularly interested on the intersection with even more constrained devices. So the devices that we have seen earlier were the ones on the left-hand side with high resources in terms of microprocessor, memory, storage, etc. We wanted to understand, can we do something with large language models that can be useful for microcontroller? And the most straightforward idea that we have had was to trying to tackle the extremely complex lifecycle management of these devices. Basically, when you compare this type of devices, the biggest issue that you have is the code portability. So the same code that you are running on a Raspberry Pi or in the Jetson Nano, the devices that we have seen here before, becomes even more complex when you go into the microcontroller. Because, for example, if you run NumPy, you can easily run on a Raspberry Pi, on a Jetson Nano, etc. But you cannot run it on a microcontroller. No way. There's no any CPU processing. It's very, very complex. So running machine learning on this type of devices is extremely complex. It requires even more complex conversion of the models. So from a TensorFlow, you need to make a sort of double conversion until you get a model that can be executed on this type of devices. So our idea was simple. The intersection that we wanted to analyze was, okay, large language models are somehow very good on generating code. We know that the lifecycle management from AI perspective of edge AI, tiny machine learning devices is extremely complex. We know that the operational cost of GPT, for example, API can become very expensive. Can we somehow put together these different pieces here? And essentially, the main question that we wanted to answer were the first one, what aspect of this edge AI lifecycle? When I talk about edge AI lifecycle, I'm talking essentially the usual machine learning pipeline, right? From data collection to AI inference. We do have a much more complex in this case because we need to convert the model, we need to optimize the model, we need to make it shrink it as much as possible in order to fit to devices like Arduino. I'm not talking anymore about the Raspberry Pi, something even more constrained that doesn't have a CPU, doesn't have anything like that. So basically the idea was, can we use large language models for generating the code for doing for basically going through this whole pipeline and trying to understand obviously what are the different trade-offs. So we developed a quite relatively complex framework. There is obviously some human in the loop here, and the language model, so things that we are giving somehow for granted, as well as an end device. In this specific case was an Arduino, so very well known microcontroller. And then obviously the main goal was to trying to get the data processing, the converted model, and the actual code to be executed on the end device in a successful way. And at the center of this, there was this framework, which was including many different components, from the typical machine learning software libraries. Then there are large language model supporting tools in order to try to understand, to debug the output of the language model, to monitor the language model in terms of consumption, token consumption, in terms of cost, et cetera, et cetera. And then a big part of the work was done, and I'm still working on this, trying to define the template for the prompt to be given to the language model. So this was a very extensive work. There is a lot of work going on the prompt. It's not a trivial thing. And what we have figured out in the follow-up of the work that I'm presenting here is that you can optimize a prompt for working well with GPT, for example. But then if you want to use the same prompt with DeepSeek or any other language model, things become extremely complex because it's not, the portability is very, very limited, at least at this stage. There are some attempts to kind of build the wrappers and common sort of definition language, but it's extremely complex. In our case, we define a sort of modular prompt template. We were defining the large language model role, trying to explain the task. One key aspect was how to manage the error handling. So when we produce code, it's likely that the language model will make a mistake, in which way we handle the error, and some other additional information for trying to build the context in the best possible way. And this is just an example here with the context. You're explaining that you are an expert in Edge AI and this and that, etc. And in the task instruction, you take information about the hardware device that you are going to handle. In this case, Arduino. You're explaining what kind of model, what kind of code you need to generate, etc., etc. The prompts were very, very extensive. And the framework essentially takes care of the data processing, the model conversion, and the sketch generator. The sketch is essentially the executable code that you're running in your Arduino. And after quite a lot of work, basically, we were able to make a proof of concept with a computer vision based model for very simple fruit identification on our Arduino. So very, very tiny and constrained devices. Just to give you some idea about how this sketch generation lifecycle works, there are multiple steps. After the input from the user, you have a sort of a different iteration with large language models. And the key aspect here is that if you have some error, you need to somehow kind of start to deal with the language model and provide useful information in such a way that the error is then solved. The final goal is to get the executable code that work well in our Arduino. If we are curious online, again, I can share the slides afterwards. You can find demos for this model quantization and conversion and the sketch generation. You will see that the large language models will fail a few times in compiling the executable code, but thanks to the error handling mechanism that we implemented, eventually was able to successfully generate the code for running on the language model. And obviously, we were also interested to understand what was the success rate of GPT in this case, and the actual cost for running all these. Just to give you some estimation, this was we evaluated the data processing, the sketch generation, and the model conversion. We got a very good success rate for data pre-processing, meaning that we were providing the data set, quite extensive data set, and language model was able to clean it, remove, the usual data engineering and data processing tasks. Very successful, even more successful in the model conversion. So we are able to convert a TensorFlow model to a model that can run on Arduino. So shrink it from X megabyte to few bytes. So quite impressive work. But this executable code, the sketch generation was not very successful. Still, it was still good. I mean, approximately 30%. And we were limiting the attempts to 5. So after 5 iterations with the language model, we didn't want to spend much money. But after 5 iterations, we were stopping the interaction with the language model. But just to give you an idea, in the case of successful operation in all the three in the 3 stages, you can see in the first column that on average in less than 2 minutes you're able to give a data set through our framework to the language model, convert the model, and build the code for performing this fruit classification in less than 2 minutes. So that's quite impressive, especially when it comes, our main target is also trying to support whoever doesn't really have the engineering or data science background for doing all these different steps, right?
So do I understand correctly, you used LLMs to generate code to implement LLMs?
No, it's not. The code that was executed on the Arduino was object detection.
Object detection.
Yes.
But you could maybe also
that's
develop LLMs.
One of our plans.
Sounds a bit scary, actually.
One of our plans is to look at, for example, transformer-based. Yeah. Obviously, you wouldn't be able to run it on Arduino in such constrained devices yet, but in devices like Raspberry Pi, we did this work. It's proved, but that's one possibility. Another interaction that we are now seeking is the small language model and large language model interaction. So can we somehow use a local language model for basically increasing actually the success rate, increasing the success rate when it comes to the sketch generation. For example, the small language model can abstract some local information from the hardware that you perhaps don't have available if you just share some random data with the large language model. So all this kind of trade-off. Also here there is a lot of interesting aspect to be taken into account. And just to give you some idea, we were looking at again this execution time, how long it takes for the whole life cycle, but also the operational cost. Here you can see that some successful sketch generation was costing something like $0.15. You say like that's nothing, but if you think on hyperscale, let's suppose that the city of Helsinki will implement this for updating the smart city sensor deployed in our city, that becomes a quite big cost. So that's something that we are also trying to tackle. And trying to extend this work, as I mentioned, fine-tuning the large language model, integrating external tools, not necessarily AI-based tools. And as I just mentioned, this is sort of interaction between the small language model, large language model for trying to improve the sketch, especially the executable code generation. There's also like a publication related to this if you're curious, and we are heavily working on this area. I have also some possible federated learning overlap here in the next few slides. Can I still go for a few minutes?
Yeah, sure.
Okay. Yes, please. You mean as a large language models? Yeah, you can run easily object detection with very good performance, speech to text, quite many nowadays. Yes, yeah, that was a CNN network. Yeah. So there has been some attempt, not in Arduino. There is some ST microelectronics, which is nowadays you can't find it because it's been one of the few microcontroller yes, exactly, in which you can run even some transformer, so not really full generative AI model, but you have some obviously the quality of the responses are very, very poor. So I don't know. Also, when you run a small language model on Raspberry Pi or Jetson Nano, even this the pre-version of DeepSeek, if you ask where Cristiano Ronaldo has played, you would get Barcelona or Inter, something completely hallucinated. So the quality is still to be taken. You can't do very, very complex thing, right? Just to conclude on this generative AI area overview, with this involvement of end device, the last piece of work that we are doing is this sort of, and mostly for trying to reduce as much as possible the cloud dependence, right? We don't want to give up data. Nowadays, people realize that, you use a large language model, a GPT type of, and you don't think about what you're typing there, you're giving up. That's a good topic for you, right? You are giving up any type of data, right? You don't think, like, you just use it as a Google, and you might also release some sensitive information, right? So what we are trying to do here, and this is the work I'm currently doing with some colleague in Nokia Bell Labs Cambridge, is essentially trying to essentially look at smaller language models and trying to find a way to make the collaboration with large language model successful. Like, can we execute part of our language-based or request or any kind of a type of a request we are doing with these tools nowadays locally, and then rely on cloud only in case my resources are not good enough, the quality of the response I'm getting are not good enough, etc., etc. There are different trade-offs there: cost, performance, privacy, as I just mentioned. And the very basic idea now that we are trying to do is essentially trying to understand how to classify queries. Like, how can you classify a query that is extremely complex, that locally cannot be computed, and I need to let's say offload it to to a larger model, and this type of collaborative approaches that can raise in these similar scenarios, like this distributed edge computing. The type of scenarios we are looking are, in the smart cities environment, where you can have different agent, different models specialized on multimodal visual data, or some fine-tuned to get some specific information about security in this specific area. This type of collaboration that doesn't rely on, it's somehow more trusted, and it doesn't rely on this centralized service. And we did some very basic experiment here, trying to develop in a similar test, but it's not exactly the same as the one we have at the University of Helsinki. Try to understand to understand the given certain pattern of requests that we do to this type of edge devices that are executing language model, to what extent we are using, taking consideration some random distribution in the nodes, the heterogeneity, etc., etc. To what extent we are able to minimize as much as possible the request that we offload to cloud-based GPT, because eventually that's what we want to do. We don't want to give up too many data. We are also aware that we cannot fully rely on edge computing, because you don't get satisfactory answer as you would get from GPT. We must be realistic. Just to give you an idea, the Arduino project, we extended beyond GPT. We tested many large language models, from the Codstral Llama 70 billion, very good ones. Still, there's no the highest success rate we have been able to reach is 11%. So like 20% less than GPT. And there has been only one large language model. When it comes to DeepSeek, big number of billion parameter, or even big models, the success rate the majority of the time in sketch generation was 0. So not impossible to get any closer to GPT. So the idea would be to look at this sort of query routing between edge and and cloud, trying to minimize this cost and cloud dependence. And I guess that here there are plenty of learning directions, because when it comes to the first work that I show, there is obviously a lot of work that can be done on fine-tuning the prompt itself. Like we have different type of devices, so each prompt can be self-adaptive based on the local data and the local environment that each device has, and the same for these model routing policies, because you can actually have federal learning to train some sort of routing classifiers locally in each of these nodes. And finally, when it comes to this lifecycle management, software generation, you can have some, this incentive mechanism or feedback loop, again, trying to take advantage of the local knowledge that you have in the devices. So these are very like a lot of ongoing work. There are a lot of things that can be done, obviously extension. But that's pretty much it about my presentation. Thank you for the attention. If you have any question, I'm here. Thanks a lot. Thank you.
Any questions?
Please.
What if regarding last thing, for example, batch that come to say local,
yes,
and then like send somebody to store and kind of like local links based on whatever it was.
So you mean like local batching for and using the small language model local?
So for example, let's say the particular element is deployed in a part, and people usually ask about, say, safety.
Oh, yes, yeah.
And then you really in particular that from another.
Yes. So that's one of the things that we are also looking when it comes to this classification of queries. Our assumption is that we will eventually have a different, we call them agent or whatever, specialized language model that are, as I said, specialized to some specific topic. And the main is not so trivial to classify your query. We have been running some tests, for example, on using large language model for classifying queries. I haven't included the results here in this presentation, but we realized that, for example, that we were comparing the classification capabilities of language model from GPT to very small language model. And we realized, for example, that verbose prompts were working very well with the GPT and bigger models. So in case of verbose prompt, you submit a query, the models is capable to redirect to the right model. But on the other hand, we realized that for smaller model, the verbosity was actually a problem. So we had to kind of having classification. There are many trade-offs. It's not easy, and the success rate of classification for small language model was approximately around 40% for some of the model. Some even good one like this fee model from Microsoft was 0, for example. So there are many trade-offs and different optimization aspects that can be done there.
Yeah, I was wondering, how do you use the term model when you say a TensorFlow model? Is this a specific architecture, a network structure, or a piece of code that is written in TensorFlow?
It's both. I'd say everything, right?
Yeah.
So from the code to the model that you ship on the device itself. Yes.
You also mentioned model conversion. So is it in a sense a translation between programming languages or
no? There
packages?
Basically the when you have a TensorFlow model, it has big size that essentially wouldn't fit in a Raspberry Pi or simply the other capabilities of these devices do not support some operations like in the neural network. So you need to prune the model, you need to make some distillation, etc. That's what the model conversion is about. Yeah.
Thank you.
Thanks.
Any other questions? If not, yeah, then thanks again.
Thank you. Thanks a lot. Thank you.
Have a nice evening.